Welcome to the Deep Dive. We're the place you come to really get into the thick of complex topics, pulling apart the dense sources to give you the core knowledge.
Glad to be here.
Today, well, we're strapping ourselves in for a journey deep into geological time. We're tackling something pretty mind-bending: the Earth's magnetic field reversal, the ultimate planetary flip-flop.
It's an absolutely phenomenal topic. It really shows you just how dynamic our planet is, constantly changing beneath our feet, even on these, massive scales.
And we've dug deep into the research for this one.
Oh, yeah. We've got a stack of really remarkable material. It gives us pretty much the complete story, right from those early kind of dismissed discoveries in volcanic rocks.
Which people didn't know what to make of at first.
Not at all the way through to the really sophisticated physics of the planetary dynamo, the engine driving these flips.
Yeah.
And maybe most importantly for everyone listening.
What does it actually mean for us, for life?
Exactly. We'll look at the actual effects, or maybe the lack thereof, on life here on the surface.
Right. So our mission today is to take this huge, sprawling geological story and we'll break it down for you, the listener, make it accessible, but also hopefully absolutely fascinating.
Let's start with the real basics then, because clarity here is key.
Definitely. We need to be super clear. We are not talking about the geographic North Pole moving around, the spot our planet spins around. That axis is stable.
That's a common confusion. We're focused purely on the magnetic poles, the ones your compass needle points to. We're talking about swapping places entirely.
North becomes south, south becomes north. Magnetically speaking.
That distinction is absolutely vital. So a geomagnetic reversal, by definition, is that complete interchange of magnetic north and magnetic south. It's a 180-degree flip in the main magnetic field, the dipole field.
And geologists have terms for the periods in between flips.
They do. We talk about chroms. A chron is simply a period, could be long or short, where the polarity stays put. It's either normal or reversed, but it's stable.
Okay, and right now, today, we're in a normal period.
Precisely. We are currently living in a period of normal polarity. That just means the north magnetic pole is, broadly speaking, near the geographic North Pole, like it is now.
And the opposite.
When the field is flipped, which, it has been for huge stretches of Earth's history, hundreds of millions of years if you add it all up, we call that a period of reverse polarity.
So it's basically a binary switch recorded in the rocks over eons.
That's a good way to put it. A global magnetic switch, flipping back and forth through deep time.
Now, the scale of this, it's immense. But the data we have now is, surprisingly specific when you look at recent geological history.
It really is.
If we focus just on the last 83 million years or so, the research points to at least 183 full reversals.
That's the number derived from the magnetic seafloor record, primarily.
Okay, so if you just do the simple math on that, 183 reversals in 83 million years, it averages out to something like one flip every 450,000 years. It sounds kind of regular when you put it like that.
But that average, while, mathematically correct, is actually highly misleading. The timing isn't regular at all. It's clustered.
Right, it's not like clockwork.
Far from it. We can point to the most recent full reversal. That's the Brunhes-Matuyama reversal. It happened about 780,000 years ago.
So if the average is 450,000 years, and the last one was 780,000 years ago,
people jump to the conclusion, we must be overdue for another one.
Which implies some kind of cycle or predictability.
Exactly. But the deeper statistical analysis, which we'll definitely get into later, shows it's much more random than that average suggests. But let's stick with the process for now. When a flip actually starts, it's not like flipping a switch, right? It's a process.
It takes time. How long does that chaotic transition period actually last?
Well, that's one of the tricky things. The estimates vary quite a bit, making it hard for scientists to, pin down one single number from studying the rock record. There's noise, gaps.
But generally speaking,
the accepted window for a full reversal seems to be somewhere between 2,000 and 12,000 years.
Okay, so millennia. Not centuries, not instantaneous.
Definitely millennia. And if you look really closely at the four most recent ones, the ones we have the best data for, the average duration for those specific flips works out to be around 7,000 years.
7,000 years. That's not a quick flicker. That's a significant chunk of geological time where the planet's main magnetic shield is, kind of haywire.
This whole geological event of magnetic instability, yeah.
But there was a fascinating detail in the sources, something from Clements back in 2004, suggesting even that 7,000-year average isn't the whole story. It varies depending on where you are on Earth.
That's a really critical nuance. It highlights just how complex the dynamics within the core must be. Clement's research suggested the apparent duration of the reversal process might be latitude dependent.
How so? Shorter somewhere, longer elsewhere.
The idea is that the reversal might seem to happen faster or be completed more quickly when observed in rocks near the equator, so at low latitudes. But it might appear significantly longer, more drawn out, more chaotic maybe if you're looking at records from mid or high latitudes.
Huh. So it's not just the whole field weakening and flipping uniformly.
Probably not. It tells us the transition is likely a spatially complex mess. Different magnetic bits and pieces, maybe multiple poles, could be emerging and dissipating across the globe as the core fluid slowly rearranges itself into the new stable state. It's not a simple dipole flip.
Okay, so a full reversal takes thousands of years. But you mentioned earlier that sometimes the core tries to flip but doesn't quite make it. It runs out of steam.
Exactly. Those are what we call excursions. They're like the failed attempts, the almost reversals.
And it's important to distinguish those from the full ones.
Absolutely essential. Mainly because they're much shorter, often just a few hundred years, maybe up to 1,000 years or so, and they seem to happen more frequently than full reversals.
The last Champ excursion is a famous example, right? About 41,000 years ago.
That's the classic one, yes. Very well studied. Excursions are basically these temporary, quite rapid changes in the field's direction, but they just fail to lock in permanently. The field snaps back.
And the reason why they fail is tied to Earth's structure. Specifically, the fact we have both a liquid outer core and a solid inner core.
Precisely. That's the key. You can sort of picture the Earth's core as having this two-stage locking mechanism for the magnetic field. For a full reversal to happen, the flip has to succeed in both parts.
Okay.
Now, the liquid outer core, that's where the dynamo action primarily happens. It's dynamic, fluid. The magnetic field can reverse there relatively quickly, maybe on a timescale of 500 years or less, driven by that fast fluid flow.
But that's only stage one for it to stick.
For the reversal to become permanent, the new field orientation has to diffuse into and essentially flip the locked-in magnetization of the solid inner core.
And the solid inner core is much more.
That's a great way to put it. It acts like a massive anchor, magnetically speaking. The time scale for magnetic changes to diffuse through that solid iron-nickel sphere is far, far longer. We estimate it's around 3,000 years.
Ah, so an excursion, which might only last, say, 500 years?
It's just too short. The outer core flips, but before the slow-moving inner core can even begin to respond and follow suit, the conditions in the outer core change again, and it snaps back to the original polarity, stabilized by that inner core anchor.
The inner core's inertia prevents the flip from completing.
Exactly. Its magnetic inertia keeps the overall field basically anchored in the old direction, and eventually the outer core just gives up the ghost and realigns. That neatly explains why we see these shorter, more frequent blips that never quite become full reversals.
You know, what's really amazing is tracing how scientists figured all this out. This idea of the entire planet flipping its magnetic field. It wasn't obvious. It was pieced together from clues that people initially just wrote off as weird mistakes or anomalies.
Oh, completely. The story starts really quietly back in the early 20th century. There was a French geophysicist, Bernard Brunhes. He was one of the first to notice, just systematically note, that some volcanic rocks he was studying were magnetized in the opposite direction to the Earth's magnetic field at the time.
Just an oddity back then.
Pretty much. It didn't fit the picture of a stable Earth. Then, a bit later, in the late 1920s, a Japanese geophysicist, Brunhes-Matuyama, provided the first really systematic evidence.
He did more than just find one odd rock, right? He saw a pattern.
He did. Matuyama carefully observed that rocks showing this reversed magnetization weren't just random. They were all older than a certain geological age. Specifically, he found they were all from the early Pleistocene or even older periods.
So he had the first glimpse of a timeline, a dividing line in history.
Essentially, yes. He was saying, look, all the rocks younger than this point have normal polarity, like today. All the rocks older than this point have reversed polarity. It was a huge insight. But
the scientific world wasn't quite ready to accept something so radical.
Exactly. He ran into the same problem Brunhes did. People didn't really understand the Earth's core dynamics well enough. The prevailing view was much more, uniformitarian, slow, steady changes, not dramatic planetary flips. The idea was just too out there for the available physics and technology.
So it took a while for the idea to catch on. What changed?
It really took until the post-World War II boom in geophysical research, particularly paleomagnetism, in the late 1950s. By then, scientists finally had a solid grasp on the fact that many volcanic rocks, as they cool, basically take a snapshot of the Earth's magnetic field. They understood the mechanism.
And that mechanism hinges on something called the Curie temperature. Let's pause on that because it sounds crucial.
It's absolutely the physical key to the whole thing. The Curie temperature, or Curie point, is a specific temperature for magnetic materials. Above this temperature, they lose their permanent magnetic properties. They're not magnetic anymore.
Okay.
But when volcanic rock, like basalt forming from lava, cools down, its temperature eventually drops below the Curie point of the iron-bearing minerals within it, like magnetite.
And as it crosses that threshold,
As those tiny mineral grains cool past that critical temperature, they become permanently magnetized, aligning themselves with whatever the Earth's magnetic field direction and intensity is at that exact moment.
wow. So the rock becomes a fossil compass.
Precisely. It locks in a record of the ancient field. Direction, sometimes even intensity, a tiny, permanent magnetic memory.
Okay, so we have the direction locked in the rock, but to build a history, you need the date it locked in, the age of the rock.
And that was the second piece of the puzzle, the technological leap. Radiometric dating. By the late 1950s, techniques for dating rocks using radioactive decay were getting much, much better. More accurate, more reliable.
And some scientists saw the potential to combine these two things, magnetism and dates.
Exactly.
Yeah.
Alan Cox and Richard Dole, working at the U.S. Geological Survey, really grasped this. They teamed up with the geochronologist Brent Dalrymple, who was a leader in improving these dating methods. Together, they started this intense effort.
To put actual dates on those polarity changes Matuyama had seen decades earlier.
That was the goal. They wanted to measure the magnetic polarity and get a precise radiometric age for the same rock sample over and over again from sequences of lava flows. This huge effort led to the very first quantitative magnetic polarity timescale in 1959.
And apparently this wasn't just a quiet academic exercise. There was some competition involved.
That's very much so. It was a classic scientific race. There were other teams doing similar work, notably Don Tarling and Ian McDougall's group in Australia. This friendly but intense competition actually pushed the science forward incredibly quickly.
How so?
Well, it meant everyone had to be really rigorous. They were constantly checking each other's results, refining their dating techniques, improving the paleomagnetic measurements. It helped establish a really robust, verifiable timeline of flips based on these volcanic rocks found on land.
Okay, so they built the timeline using rocks on continents. But how did they prove this wasn't just some weird local phenomenon? How did they show it was truly global?
That clinching evidence came from a completely different environment, the deep ocean floor. A group led by Neil Opdyke, working at the Lamont Doherty Earth Observatory, started analyzing long cylinders of mud deep-sea sediment cores.
What did they find in the mud?
Deep-sea sediments accumulate slowly, layer by layer, and they contain tiny magnetic mineral grains that settle through the water. As these grains settle, they tend to align themselves with the Earth's magnetic field at the time of deposition, just like the minerals cooling in lava.
So the mud layers also record the field.
Yes, and Opdyke's group found the exact same sequence of normal and reversed polarity intervals in those deep-sea mud cores as Cox, Dole, and Dalrymple had found in the volcanic rocks on land.
Wow. Same pattern, different place, different type of record.
It was the definitive proof. It showed, beyond any reasonable doubt, that these magnetic reversals were synchronized global events. The entire planet's field was flipping together.
Okay, this next part of the story is amazing. Because figuring out the history of these flips didn't just, solve the mystery of the reversals themselves. It accidentally provided the killer evidence for something even bigger: continental drift and seafloor spreading.
It really was the scientific breakthrough that tied everything together. A total game changer for Earth science.
So what happened? How did reversals prove continents move?
Well, throughout the 1950s and early 60s, research ships were crisscrossing the oceans, towing magnetometers. Often this was related to Cold War stuff like submarine detection, but they were collecting huge amounts of data on the magnetic field strength over the seafloor.
Just raw data initially.
Just raw data. But then scientists started plotting this data onto large maps looking for patterns. And what emerged, particularly over the mid-ocean ridges, wasn't random noise at all. It was stunningly regular. Exactly. Remarkably regular and continuous magnetic stripes, as the papers described them. These stripes of slightly stronger and slightly weaker magnetic field ran parallel to the mid-ocean ridges, and crucially, they were symmetrical on either side of the ridge crest.
Like a barcode printed on the ocean floor?
That's a perfect analogy. a magnetic barcode recording Earth's history. The explanation came in 1963, published by two British geophysicists, Frederick Vine and Drummond Matthews. It's now famously known as the Morley-Vine-Matthews hypothesis.
And we should probably mention, fairness demands it, that a Canadian scientist, L.W. Morley, had actually come up with the same idea independently a bit earlier.
Yes, sadly his papers were rejected by the major journals at the time. A real shame, historically. But the hypothesis itself was the key.
What was the core idea? How did it connect reversals, stripes, and spreading?
It brilliantly combined two cutting-edge ideas. First, Harry Hess's theory of seafloor spreading the idea that new oceanic crust is constantly being created at mid-ocean ridges and spreading outwards. Second, the now established geomagnetic reversal timescale that Cox and others had worked out.
So put together.
The insight was this. As the new volcanic rock erupts at the mid-ocean ridge and cools down through that Curie temperature.
It gets magnetized.
Right, it gets magnetized in the direction of whatever the Earth's field is doing at that exact moment. If it's normal polarity, the rock gets normal polarity. If the field flips to reversed, the newly forming rock at the ridge gets reverse polarity.
And because the seafloor is constantly spreading away from the ridge,
You create these bands, these stripes, of alternating magnetic polarity, like a tape recorder running at the ridge crest, recording the flips. And because the spreading happens on both sides of the ridge.
you get perfectly symmetrical stripes mirrored on either side.
Exactly. A stripe of normal polarity on one side has a matching normal stripe at the same distance on the other side. Same for reverse stripes. It was undeniable proof of seafloor spreading.
And by dating the reversals from the land rocks, they could now figure out how fast the seafloor was spreading.
Precisely. They could measure the distance from the ridge to a particular magnetic stripe, representing a known reversal age, and calculate the spreading rate. It turned continental drift from a controversial idea into quantifiable plate tectonics. It absolutely revolutionized geology.
Okay, but that magnetic stripe proof relies on oceanic crust. And the oceans are constantly being recycled through subduction. What's the oldest seafloor we can actually study this way?
That's a key limitation. Because of subduction, there's basically no seafloor older than about 180 million years still around today. So the magnetic stripe record essentially cuts off there in the mid-Jurassic.
So how do we peer back further? Before 180 million years ago, we need continental rocks again.
We do. To get glimpses of the field's behavior in deeper time, we have to rely entirely on continental rocks. Specifically, we look at older sedimentary rocks. Things like limestones, shales, sandstones.
How do they record the field? They're not volcanic.
They're not volcanic, but they often contain tiny, sometimes microscopic grains of iron-rich minerals, things like magnetite or hematite, that were eroded from other rocks and washed into the basin where the sediment was accumulating.
Ah, like the deep sea sediments.
Exactly the same principle. As these tiny magnetic grains settle through the water column or were deposited, they would physically align themselves with the Earth's magnetic field at that time. Then, as the sediment got buried and lithified into rock, that alignment gets locked in.
That sounds incredibly delicate. Is that signal reliable after hundreds of millions of years of burial and potentially deformation?
It requires incredibly careful work. Paleomagnetists have developed sophisticated lab techniques to isolate that original detrital remnant magnetization and, crucially, to perform tests to make sure it hasn't been reset or altered by later chemical changes or heating events. It's painstaking stuff.
But when it works?
When the data is robust, it allows us to push the paleomagnetic record back maybe to 250 million years ago, sometimes even earlier, though the quality tends to decrease as you go further back.
And this older data, it's not just for like historical curiosity about reversals. Does it have practical uses for geologists?
Oh, absolutely. It's a critical tool, especially for dating and correlating rocks. Remember, the Earth's magnetic field is global. A reversal happens everywhere at essentially the same time.
A worldwide time marker.
Exactly. So the established geomagnetic polarity timescale, GPTS, which combines the seafloor data with the best land-based data, acts as a universal reference.
How would a geologist use it in the field?
Let's say you're studying a thick sequence of ancient sedimentary rocks, maybe somewhere in South America. And maybe these rocks don't have good index fossils for dating. If you carefully measure the magnetic polarity up through that sequence, you might find a specific pattern, say normal reversed, normal reversed.
Okay.
You can then compare that unique pattern to the known GPTS. If you find a match, bingo. You can assign accurate ages to the different layers in your rock sequence. It's incredibly powerful for correlating rock units across continents, especially in metamorphic or igneous terrains where fossils are useless. It gives us a global chronological framework.
So this GPTS, the Geomagnetic Polarity Timescale, it sounds like a monumental achievement of geology, a complete map of the planet's magnetic pulse over millions of years.
It truly is. A massive undertaking, constantly refined as new data comes in. The current scale, synthesizing everything from seafloor magnetic anomalies to radiometric dating of lavas on land, details, as we said, 184 distinct polarity intervals, meaning 183 reversals just in the last 83 million years.
But you emphasized earlier that the average spacing, that 450,000 years, is misleading. Looking at the actual GPTS, you see wild swings in how often the field flips.
Massive swings. It's anything but steady. The rate of reversal fluctuates dramatically through time.
Our sources give some really striking examples of this variability, like around 72 million years ago, the field was going crazy.
Yeah, flipping back and forth really rapidly then. The data shows about 5 reversals packed into just 1 million years during that period. That's incredibly fast, an average of only 200,000 years between flips.
And then there was another burst of activity even more recently.
Even more intense, centered around 15 million years ago. There was a period lasting about 12 million years, where the Earth underwent no fewer than 51 reversals.
51, that's an average of, what, less than 250,000 years per interval?
Even faster than the earlier period. And within that frenzy, we have evidence for times when the flip-flop rate got even more extreme. There's one documented case of 2 full reversals occurring within a span of only 50,000 years.
Wow, that's almost continuous instability.
It really highlights the chaotic nature of the dynamo sometimes. But then the GPTS also shows the complete opposite. These periods of intense activity are offset by incredibly long stretches where the field just stayed put, refused to flip for millions, even tens of millions of years.
The eras of magnetic calm, these are the supercrons.
Exactly. A supercron is formally defined as a polarity interval, either normal or reversed, that lasts for at least 10 million years without any reversals.
10 million years of stability, that's a long time.
A very long time. And we have 2 really well-established, undeniable supercrons in the geological record.
Okay, let's break those down. The first one happened during the age of dinosaurs, right?
That's the Cretaceous normal supercron, often just called C34 by geologists. This was a truly enormous block of time. It lasted for about 37 million years.
37 million years. When was this exactly?
Roughly from 120 million years ago up to about 83 million years ago, spanning a large chunk of the Cretaceous period. And during that entire time, the Earth's magnetic field had normal polarity, just like today's field, uninterrupted normal polarity.
What's fascinating is how it began and ended. Did the field just suddenly stop flipping?
Not quite suddenly. The data suggests the reversal frequency was actually steadily decreasing for millions of years before the supercron started. It's like the dynamo was gradually winding down its flipping activity. Then it hit 0 flips for 37 million years.
And after it ended?
After C34 ended around 83 million years ago, the reversal frequency started to slowly, generally increase again, leading towards the more rapid flipping rates we see in the later Cenozoic. It's a fascinating long-term cycle of activity.
Okay, that's the Cretaceous normal supercron. What was the other one? You said it was even longer.
Even longer, and crucially, it had the opposite polarity. This is the Kieman reverse supercron.
Kieman reverses.
This was an incredibly long stretch of magnetic stability, lasting for more than 50 million years. The best estimates place it from about 312 million years ago to roughly 262 million years ago, spanning the late Carboniferous and much of the Permian period.
And the reverse part means?
It means that for that entire 50 million year plus duration, the Earth's magnetic field had reversed polarity. If you were around then with a compass, north would have pointed south.
Wow. Why is it called Kieman?
It's named after the town of Kiama in New South Wales, Australia. That's where volcanic rocks showing this extremely long period of reverse polarity were first studied in detail and documented back in the 1920s, actually predating the full understanding of reversals.
So it seems like once the Earth's dynamo settles into a particular state, normal or reversed, it can sometimes just get stuck there for an incredibly long time.
Absolutely. It suggests that the conditions within the core, the heat flow, the convection patterns, must have been exceptionally stable during those supercron intervals to suppress the flipping mechanism for so long.
But not every suspected long, quiet period has turned out to be a true supercron, right?
Yeah.
Have there been some proposed ones that didn't pan out?
Yes, there have been a few candidates that were later questioned or dismissed as our data got better. One example is the proposed Moyero reverse supercron.
Moyero.
Yeah.
When was that supposed to be?
It was thought to have occurred during the Ordovician period, maybe lasting over 20 million years, from about 485 to 463 million years ago. The initial evidence came from Siberia,
But
but subsequent, higher quality paleomagnetic studies from other parts of the world sampling rocks of the same age just didn't find evidence for such a long, uninterrupted reversed period. The global picture didn't support it.
so maybe a local magnetic quirk or a problem with the dating of the original rocks.
Exactly. It seems more likely it wasn't a true global superchron. Maybe a regional magnetic feature, or perhaps gaps in the Siberian rock record were misinterpreted.
Okay, and what about the Jurassic Quiet Zone? The name itself sounds like a superchron, a period of magnetic quiet. But you mentioned it's not considered one anymore.
That's right. The Jurassic Quiet Zone is a specific area of the ocean floor, particularly off the Atlantic coast of North America and Africa. When ships first mapped the magnetic anomalies there, in crust older than about 160 million years, the signals were very weak, very low amplitude, a quiet zone.
So naturally, people assumed the field had stopped reversing during that time.
That was the initial interpretation, yes. It looked like a superchron. However, paleomagnetists studying Jurassic rocks on land from the same time period did find evidence of reversals, so there was a conflict.
What resolved the conflict? Why is the signal quiet over the ocean floor then?
It turns out the quietness is likely due to a combination of other factors, not a lack of reversals. Two main things. First, studies of paleointensity, the strength of the ancient field, suggest that the Earth's magnetic field was generally quite weak globally during much of the Jurassic, roughly between 130 and 170 million years ago.
Okay, so the field was weak to begin with.
Exactly. Second, those particular parts of the Atlantic Ocean floor that make up the quiet zone formed when the Atlantic was just starting to open, and they are now incredibly deep, buried under thick layers of sediment.
Ah, so you have a weak original signal recorded in rocks that are now very deep underwater.
Right. By the time that already faint magnetic signal travels from the deep basalt crust up through kilometers of water to reach the magnetometer being towed by a ship at the surface, it's severely attenuated, weakened.
Like trying to hear a whisper from across a huge stadium.
That's a good analogy. The signal looks quiet simply because it was weak to start with, and it has traveled a long way. So it's now understood as an observational artifact of low field intensity and great ocean depth, not a true superchron where reversals stopped.
Okay, that makes sense. Let's shift gears a bit and talk about the statistics of these reversals. We see this huge variability, rapid flipping, long superchrons. Does the overall pattern tell us anything about the underlying mechanism? Is it predictable at all?
Well, the detailed statistical analysis of the reversal record is fascinating, and the main conclusion is pretty stark. Reversals appear to be statistically random.
Random, meaning completely unpredictable.
In terms of timing, yes. If you analyze the lengths of successive polarity intervals in the GPTS, you find there's no correlation between the length of one interval and the length of the next one.
So the Earth doesn't remember how long the last interval was. A long one doesn't mean the next one will be short, or vice versa.
Exactly. The system seems to have no memory in that sense. Also, over the long haul, there's no inherent preference for normal versus reverse polarity. The Earth seems equally happy in either state.
And this randomness is important because
Because it strongly contradicts claims you sometimes hear about reversals happening with a regular periodicity, like a fixed cycle. The data just doesn't support strict cycles.
if the timing is random, how do scientists model it? You mentioned Poisson processes.
Yes. Initially, the simplest models used were based on Poisson processes, which are standard for modeling random independent events occurring over time, because the average rate of reversals clearly changes. Think superchrons versus rapid periods. They use what's called a non-stationary Poisson process, meaning the average rate itself can vary.
But you hinted it's more complex than simple Poisson randomness.
It seems to be. When you dig deeper into the statistics, some subtle patterns emerge. For instance, there appears to be a slight inhibition effect.
Inhibition, meaning what?
Meaning that immediately after a reversal happens, there seems to be a slightly reduced probability of another reversal occurring for maybe the next few tens of thousands of years.
Like the core needs a brief cool-down period or time to reset itself before it can flip again.
That's one way to think about it, yeah. Like it needs to reorganize or maybe recharge its structure before it's capable of undergoing another major flip. It introduces a small element of short-term memory or non-randomness.
And there are even more sophisticated models, something about Levy distributions and chaos.
Right. This gets into some advanced statistical territory. But researchers found that the distribution of the lengths of polarity intervals doesn't follow a simple bell curve or exponential decay like a basic Poisson process. Instead, it fits better with something called a Levy distribution.
Okay, Levy distribution. What does that imply in sort of plain English for how the field behaves?
Levy distributions are characteristic of systems that exhibit bursts of activity separated by long periods of inactivity, and crucially, they often arise from processes with long-range correlations or memory. In this context, it suggests the extreme lengths of the supercrons and the flurries of rapid reversals aren't just random outliers, they are an inherent feature of the underlying dynamics. The system has a tendency towards these extremes.
And this links to the idea of chaos.
Exactly. This kind of statistical behavior, the randomness punctuated by inhibition and Levy statistics, is highly consistent with a system that is deterministic but chaotic.
Deterministic but chaotic, meaning it follows rules but is still unpredictable.
Precisely. It means the behavior of the core and the magnetic field is governed by fundamental physical laws, fluid dynamics, electromagnetism. It's not just random chance pulling numbers out of a hat. However, the system is so incredibly sensitive to tiny variations in its initial conditions, the exact flow patterns, temperature fluctuations deep in the core, that its long-term behavior becomes practically unpredictable, just like weather forecasting beyond a couple of weeks. The underlying physics is known, but the outcome is chaotic.
Okay, so we've established the average reversal takes thousands of years. Geologically fast, but still a long time in human terms. But buried within that average are hints of something much faster, right?
Yeah.
Some evidence suggests parts of the transition can happen at speeds that seem, well, almost impossibly fast for a planetary scale system.
That's definitely one of the hottest areas of debate and research in paleomagnetism right now. While the full process takes millennia, the actual transition period, when the main dipole field is weak, seems to be incredibly chaotic.
What does that chaotic state look like? Does the field just switch off?
No, it doesn't vanish completely. That's a key point. But the main simple north-south dipole field collapses, its strength plummets. And what seems to happen is that the field becomes much more complex, non-dipolar. You might get multiple local magnetic poles popping up transiently all over the globe. It's magnetically messy until the core eventually settles back into a stable dipole state, either normal or reversed.
And within that messiness, some changes can happen incredibly quickly. Tell us about the famous Steens Mountain study.
Ah yes, Steens Mountain in Oregon. This involves analyzing the magnetic records locked into a sequence of lava flows dated around 16.7 million years old. When scientists first meticulously measured the direction of the magnetic field recorded layer by layer through these flows, which erupted relatively quickly one after another,
They found something extraordinary.
they found evidence suggesting the magnetic field direction had shifted at an astonishing rate, possibly up to 6 degrees per day, during brief parts of the reversal captured in those lavas.
6 degrees per day. That sounds unbelievably fast for the entire planet's magnetic field. How did other scientists react to that initially?
With a great deal of skepticism, frankly. The immediate reaction from many in the field was, that can't be right. There's a concept that the Earth's mantle, lying between the core and the surface, should act like a filter.
A filter? How?
The mantle has some electrical conductivity. It's not a perfect insulator. The thinking was that this conductivity should effectively dampen or smooth out any really rapid magnetic fluctuations originating in the core. Any changes happening on timescales of just days or months should get smeared out by the time the signal propagates through the mantle to the surface where we can measure it. 6 degrees per day seemed too fast to make it through the mantle filter.
But the Steens Mountain results held up.
They did. The researchers did more work, refined their techniques, and the results remained robust. Then, crucially, other studies started finding similar evidence.
Like the one at Battle Mountain.
Exactly. A different team, sampling different lava flows nearby in Battle Mountain, Nevada, dated to about 15 million years ago, also found evidence consistent with extremely rapid field changes. Specifically, they documented a very brief interval, maybe lasting only several years, where the magnetic field direction swung by over 50 degrees.
So multiple lines of evidence pointing to these bursts of speed.
Yes. This repeatable evidence from different locations and slightly different times really forced the community to reconsider. It strongly suggests that the fluid motions in the outer core can be incredibly dynamic, and that these rapid changes can sometimes be recorded at the surface, perhaps bypassing the mantle filter more effectively than previously thought. Or maybe the filtering effect isn't as strong.
So if parts of a reversal can be that fast, what's the shortest time documented for a complete reversal, start to finish?
Well, pushing the boundaries even further, there was a report in 2018 that documented evidence for a full polarity reversal that might have lasted only 200 years in total.
200 years. That's practically instantaneous, geologically speaking.
It is, but we absolutely have to balance that against other evidence. For example, a very detailed study published in 2019 looking at the most recent major reversal, the Brunhes-Matuyama, 780,000 years ago, came up with a much longer duration estimate for that specific event, around 22,000 years.
22,000 years versus potentially 200 years, that's a huge range.
It tells us the speed of reversal is likely not constant. The core seems capable of both very gradual, drawn-out transitions and these incredibly rapid, almost catastrophic shifts. The style might vary from one reversal to the next, depending on the exact state of the core at the time.
This all inevitably leads back to the engine driving the whole process, the planetary dynamo itself. Remind us how that works.
So the Earth's magnetic field is generated by dynamo action. Deep inside the planet, we have this huge sphere of molten iron and nickel, the liquid outer core. It's incredibly hot, and it's convecting, churning around, due to heat escaping from the even hotter solid inner core.
Like a boiling pot of water, but on a planetary scale and made of metal.
That's a decent analogy, yeah. And because this convecting fluid is molten metal, it's electrically conductive. As this conductive fluid moves and swirls, it generates powerful electrical currents, vast loops of current.
And moving electric currents create magnetic fields, basic physics.
Exactly, Ampere's law. Those massive electrical currents create the Earth's magnetic field. It's a self-sustaining process. The motion generates the field, and the field influences the motion. That's the dynamo.
And the amazing thing is, we haven't just theorized this. We've actually modeled it on computers and seen it work, right? Seen it reverse itself.
That was a monumental achievement in geophysics. The development of sophisticated numerical simulations, particularly the model pioneered by Gary Glatzmeyer and Paul Roberts in the 1990s, was revolutionary.
What did their model show?
They managed to create a computer model that simulated the physics of the outer core, the fluid dynamics, the rotation, the heat flow, the electromagnetism. They let it run, simulating tens of thousands of years of Earth time. And not only did their model spontaneously generate a magnetic field that looked remarkably like Earth's,
It flipped.
it flipped. The magnetic field in their simulation reversed its polarity all by itself, without any external forcing. It showed conclusively that geomagnetic reversals are not some mysterious add-on. They are a natural, emergent property of the fundamental physics governing the core. They arise spontaneously from the underlying chaotic dynamics.
And this isn't just computer theory anymore, it's been seen in labs too.
Yes, adding more confirmation, similar self-generation, and even reversal behavior has been observed in laboratory experiments using liquid metals, like the VKS2 von Karman sodium experiment in France. They managed to create a small-scale dynamo in swirling liquid sodium that could spontaneously reverse.
It's interesting to contrast Earth's dynamo with the Sun's. The Sun also has a magnetic field that reverses, but it seems quite different.
Very different in timing and behavior during the flip. The Sun's main magnetic field reverses much more regularly, roughly every 11 years, tied to the solar activity cycle. But the key difference is what happens to the field strength during the reversal.
How does it differ?
When the Sun's field reverses, the overall magnetic activity and intensity actually increase dramatically. Solar maximum, with lots of sunspots and flares, coincides with the reversal. But on Earth, as we've discussed, geomagnetic reversals happen during periods when the field strength is already low. The instability, the flip, seems to occur when the main dipole field is weak and vulnerable to being overthrown by the core's chaotic motions.
Okay, so the Glatzmeyer-Roberts model strongly supports the idea that reversals are an internal process driven by core dynamics, but there's always been this alternative idea floating around. Could something outside the core trigger a reversal?
Yes, that's the external trigger hypothesis. It's been proposed by various scientists over the years, perhaps most prominently by Richard A. Muller. The core idea, excuse the pun, is that maybe the dynamo doesn't just flip on its own. Maybe it needs a nudge from the outside.
A nudge from what? What kind of external events are we talking about?
The proposals vary. Some suggest a truly massive meteorite impact hitting the Earth's surface could send shockwaves deep enough to disrupt the flow in the outer core. Others propose that processes within the mantle could do it, perhaps the arrival of a huge cold slab of subducted oceanic crust sinking all the way down to the core mantle boundary, chilling the core locally and changing convection. Or maybe the opposite. The initiation of a giant mantle plume rising from the core boundary could disrupt the flow.
And the proposed mechanism is that this disruption, essentially, short-circuits the dynamo.
Sort of. The idea is the external event disrupts the established flow pattern that maintains the stable field. This could cause the main field to decay or turn off temporarily. Then, as the core recovers and the dynamo restarts, it has a roughly 50-50 chance of spontaneously locking into either the normal state or the reverse state. The external event triggers the collapse, and the subsequent state is random chance.
It sounds plausible on the surface. Does it hold up?
Well, the sources we looked at are pretty clear. This external trigger mechanism generally doesn't work well in quantitative physical models. The core and mantle seem to be too decoupled, both thermally and mechanically, for surface or mantle events to exert enough focused, sustained influence on core flow to reliably trigger a reversal. The energy transfer just isn't efficient enough.
And is there any actual evidence correlating known major events with reversals?
That's the other major weakness. The evidence for correlation is very weak or simply non-existent for the biggest potential triggers.
The classic test case being the dinosaur extinction.
Exactly. The Chicxulub impact event, 66 million years ago, was arguably the most dramatic short-term geological event in the last 100 million years. If any external event was going to trigger a reversal, you'd think that would be it. But the paleomagnetic record shows no evidence whatsoever for a magnetic reversal associated with that impact. The field was stable across that boundary. That's a pretty strong argument against impacts being major triggers.
So the scientific consensus remains pretty firm?
Overwhelmingly, yes. The consensus, strongly supported by the success of the numerical models and the lack of correlation evidence, is that geomagnetic reversals are almost certainly a spontaneous manifestation of the Earth's internal core dynamics. They're born from the chaos within.
Okay, this leads us inevitably to the big question for us living on the surface. Does this planetary magnetic flip-flop actually affect life? Is there any link between geomagnetic reversals and mass extinctions?
Ah, the million-dollar question. Early on, especially when people were searching for patterns in periodicity and reversals, there were definitely theories trying to link flips directly to major extinction events in the fossil record.
Based on finding a reversal and an extinction happening around the same time?
Sometimes, yes. But often these proposed correlations were based on, well, flawed claims of periodicity in the reversals or on geological dating that wasn't precise enough to really establish simultaneity.
And testing this rigorously is hard.
Extremely hard. If you're looking for links to extinctions of large animals, like dinosaurs or mammals, the fossil record is often quite sparse. Finding enough fossils precisely dated right across a reversal boundary is very difficult.
What about microfossils? Things like plankton in the oceans. Their record is much more complete, right?
It is much more complete, which is why most studies have focused there. But even the microfossil record has pitfalls when you're trying to prove a causal link to reversals. The main problem is hiatuses.
Hiatuses, gaps in the record.
Exactly. Periods where sediment wasn't deposited, or where it was deposited and then later eroded away before the next layer formed. You can imagine if you have a microfossil extinction event recorded just above a reversal boundary of a sediment core, it looks like they happened together.
But maybe there was originally a long period of normal deposition after the reversal containing no extinction, and that part just got eroded away.
Precisely. The hiatus could create an artificial appearance of correlation. Disentangling genuine cause and effect from these kinds of sampling artifacts in the geological record is a major challenge.
So when scientists apply really rigorous statistical methods, carefully accounting for dating uncertainties and potential hiatuses, what's the conclusion? Is there a direct link?
The firm conclusion from the most rigorous statistical analyses is no. There is no statistically significant evidence for a direct, causal correlation between geomagnetic reversals and major extinction events. Flipping the magnetic field does not by itself seem to cause mass die-offs.
Okay, no direct cause. But you mentioned earlier a possible indirect link, something to do with the end of supercrons.
Yes, that's a more subtle and still somewhat speculative hypothesis. It doesn't link reversals themselves to extinction, but rather links the transition out of long periods of stability, the end of supercrons, to potentially disruptive geological events.
How would that work?
The idea is that during a long supercron, the core might settle into a relatively stable, maybe even sluggish state, When the conditions finally change and the core transitions back into a state where reversals are possible, perhaps that transition involves a period of unusually vigorous convection or turbulence within the core.
A kind of rebound effect?
Something like that. And this enhanced activity in the core might increase the heat flow out of the core into the base of the mantle. This could, in turn, trigger the formation of large mantle plumes or just generally lead to a period of massive, widespread volcanism at the Earth's surface.
So the supercron ends, the core gets turbulent, triggers massive volcanic eruptions.
And that massive volcanism, the lava flows, the huge amounts of volcanic gases and ash pumped into the atmosphere, could then cause major climate change and lead to mass extinctions.
So the extinction isn't caused by the magnetic field changing, but by the geological side effects of the core shifting gears.
Exactly. It's an indirect secondary link. Plausible, but still debated and hard to prove definitively.
Okay, let's tackle the other big fear that always comes up, radiation. The worry is that when the field weakens during a reversal, we lose our shield against dangerous radiation from space, right?
That is absolutely the core concern, pardon the pun again. The image is often painted of the magnetic shield vanishing, allowing deadly cosmic rays or particles from the sun, normally trapped in the Van Allen belts, to rain down on the surface, causing mutations, cancers, killing life.
It sounds pretty scary, but the science suggests it's not quite that dramatic.
Fortunately, geology and physics offer several very strong counterarguments to that catastrophic scenario. There are layers of protection.
Okay, counterpoint number one.
The field doesn't actually disappear. Paleo-intensity studies measuring the strength of the ancient field clearly show that while the main dipole field weakens dramatically, sometimes down to maybe 5 or 10% of its normal strength, it has not vanished entirely during past reversals.
There's still some field left.
Yes. And even a weak, complex field provides some protection. For the last big reversal, the Brunhes-Matuyama, estimates suggest the magnetopause, the boundary where the Earth's field meets the solar wind, probably didn't collapse closer than about 3 Earth radii from the planet's center. It shrank, but it didn't disappear. There was still a magnetic buffer zone.
Okay, so the field weakens but doesn't vanish. Counterpoint two.
The atmosphere. Our own air is actually an incredibly effective shield against most forms of high-energy radiation from space.
How does that work?
High-energy particles, like cosmic rays or solar protons, slam into the atoms and molecules, nitrogen and oxygen, high up in the atmosphere. These collisions break the particles apart or cause them to lose energy rapidly. To reach the ground, radiation has to penetrate through the entire thickness of the atmosphere, which is equivalent to about 10 meters of water or several meters of concrete in terms of shielding power.
So even if more radiation gets through the weakened magnetic field, the atmosphere mops most of it up.
Exactly. Most of the dangerous primary radiation doesn't make it down to the surface where we live. The atmosphere acts as a really robust secondary shield, regardless of what the magnetic field is doing.
Okay, and counterpoint three, this one sounds really cool. The solar wind itself can help protect us.
It's a fascinating aspect of plasma physics. Even if, hypothetically, the Earth's internal dynamo field were to switch off completely, the constant stream of charged particles flowing outwards from the sun, the solar wind, doesn't just hit an inert obstacle.
What happened?
As the solar wind flows past Earth, its own magnetic field interacts with the planet's upper atmosphere, the ionosphere, which is electrically conductive. This interaction can actually induce electrical currents within the ionosphere, and those currents generate their own weak magnetic field.
So the solar wind itself creates a temporary magnetic shield.
Essentially, yes. It's called an induced magnetosphere.
Yeah.
It wouldn't be as strong or as extensive as our dynamo-driven field, but calculations show it would still be sufficient to deflect a significant portion of incoming solar wind particles and cosmic rays, providing a basic level of shielding for the surface.
Wow. So the Earth system has multiple layers of defense. The main field, even weakened, the thick atmosphere, and even an induced field as a last resort.
It really speaks to the resilience of the planet and the biosphere over geological time. Life has survived hundreds of these reversals.
But we do have direct physical evidence that the field weakens and that radiation does increase at the top of the atmosphere during these events, right? The beryllium-10 data.
Yes, the beryllium-10 isotope is key here. It provides the clearest, most direct fingerprint of increased cosmic ray bombardment during past events.
How is beryllium-10 made?
High-energy cosmic rays, mostly protons coming from deep space, hit the upper atmosphere. They collide with nitrogen and oxygen atoms, shattering their nuclei in a process called spallation. One of the rare isotopes produced in these collisions is beryllium-10.
And this beryllium-10 then falls to Earth.
Exactly. It gets attached to aerosols, falls out of the atmosphere in rain or snow, and gets incorporated into accumulating layers, like polar ice sheets or deep-sea sediments. The amount of beryllium-10 in a given layer acts as a proxy for how intense the cosmic ray flux was at that time.
So if the magnetic field weakens, the cosmic ray flux goes up, and you should see more beryllium-10.
Precisely. And that's exactly what researchers found when they analyzed ice cores from Greenland, looking specifically at the time of the La Champ excursion, that brief failed reversal about 41,000 years ago, where the field did flip temporarily and weaken significantly.
They saw a spike in beryllium-10.
A very clear, distinct peak in beryllium-10 concentration, corresponding precisely to the time of the La Champ excursion. It's the smoking gun evidence.
And what did that peak tell them about how much the field actually weakened during that event?
By modeling the relationship between field strength and beryllium-10 production, they could estimate that during the lowest point of the La Champ excursion, the Earth's magnetic field strength likely dropped to only about 5% of its normal modern strength.
5%. That's a massive drop.
It's a huge drop, yes. It confirms without doubt that the magnetic shield weakens dramatically during these events, and that this allows significantly more cosmic radiation to penetrate into the upper atmosphere.
But the key distinction remains.
The key distinction is that while we see this clear signal of increased radiation hitting the top of the atmosphere, the consensus, based on the lack of extinction correlation and the known shielding effects of the atmosphere itself, is that this does not translate into a biologically catastrophic increase in radiation at the surface where complex life exists. The field weakens, beryllium-10 production goes up, but life, buffered by the air above, seems to weather the storm remarkably well. Hashtag tag outro.
Wow. Well, this has been an absolutely incredible journey, a true deep dive. We started with geologists noticing weirdly magnetized rocks over a century ago, something easily dismissed.
Just anomalies back then.
Right. And we followed the story through the revolutions in dating rocks, the discovery of those amazing magnetic stripes on the seafloor that basically proved continental drift,
A cornerstone of modern geology, unlocked by reversals.
to understanding the chaotic, random, yet deterministic dance of the molten iron deep in our planet's core that drives these flips. We now know they're common, they're statistically random, they usually take millennia, but sometimes they can happen astonishingly fast.
I think the most important takeaway, the real synthesis for listeners, is about perspective. This planetary flip-flop, while dramatic sounding, isn't some impending crisis foretold by averages. It's a normal, natural feature of how Earth operates over deep geological time. It's intrinsic to the dynamo.
And life seems remarkably unfazed by it all, despite the dramatic weakening of the field.
Exactly. The evidence strongly suggests that life on Earth has successfully navigated hundreds, probably thousands, of these magnetic reversals throughout its history. That layered defense system we talked about, the residual field, the incredibly effective atmospheric shield, even the backup-induced field seems robust enough to prevent any widespread catastrophe from radiation during a flip.
It really underscores the planet's resilience, doesn't it?
It's a powerful lesson in the robustness of the Earth system.
It really is. A testament to the complex physics, the self-correcting nature, maybe, of our home world.
Indeed. Which brings us to a final provocative thought, building on that idea of chaos we discussed. The sophisticated models, the statistical analysis, they all point towards magnetic reversals being consistent with a deterministic but chaotic process.
Governed by rules, but fundamentally unpredictable in the long run.
Precisely. So here's something for you to ponder. If the Earth's magnetic flip follows fixed physical laws, but its exact timing is so incredibly sensitive to the tiniest unknowable fluctuations deep within the core true chaos, what does that imply for our ability ever to predict when the next full reversal will actually begin? Even with the fastest supercomputers and the most advanced simulations imaginable.
Will that moment when the field finally starts its next big flip forever remain a surprise? Something triggered by infinitesimally small swirls and eddies of molten iron that we can never hope to measure or model perfectly.
Is true prediction impossible in a truly chaotic system? Something to think about.